Okay, the first order decomposition of a colored chemical species X into colorless products is monitored with the spectrophotometer by measuring changes in absorbance over time. Species X has a molar absorptivity constant of 5.0 times 10 to the third per centimeter molarity, and the path length of the cuvette containing the reaction mixture is 1 centimeter. The data from the experiment are given below. First question, calculate the initial concentration of the colored species. So remember, in kinetics, initial concentration means at the beginning, and this is a classic Beer's law problem, which is absorbance equals A times B times C, where A is the molar absorptivity constant. And this is something that's like color or density. It depends on the molecule involved. And B is the path length. And if you've played with flashlights or lasers at all, you know that um, the this is a view from the top, but you know, if the light is traveling through a smaller um, diameter thing rather than a larger, more light is going to get to the detector. And then C is the concentration in molarity. And so C is concentration. And I pulled up, especially for this one. So over here, um, if you look, I think it's on page 2, this equation is A, capital A equals A, little a times B times C. And then over here they explain that A is absorbance and little a is molar absorptivity and B is path length and C is concentration. And so whenever they ask you about light colored solution, and they will quite probably, there's 4 required labs that use the spec 20s. And so it's not so bad. They want the concentration. So the first thing we're going to do is the algebra, and we're going to divide both sides by little a times b. And then the interesting thing is, and they want the initial. So initially at time 0, the absorbance is zero point 0.6, and that is unitless because it's a ratio of how much light went in is the denominator, and how much light hits the detector is the numerator. So this means only 60% of the light, or zero point 0.6 of the light, came through. And then because A is downstairs, I'm going to flip it. And if you look up here again, this is how you write 5,000 if you want it to have 3 sig figs. And so another way of writing this is 5,000 with 3 sig figs per centimeter times molarity, because the -1 just means they're downstairs. And so when I come down here, I'm just going to go centimeter times molarity is up, and then 5,000 is down. And then also the path length is 1 centimeter. They told you that the cuvette length is 1 centimeter. They told you that right there. But it's downstairs, so I'm going to do the reciprocal, so 1 over 1 centimeter. And an interesting thing happens. Centimeter cancels with centimeter, and nothing cancels with molarity, but you're solving for concentration. So we're glad that that happened. And so if you do this on your calculator, you will get 1.20 times 10 to the -4 molar. So that's the answer. I'm actually going to encourage you to come up here on this problem because I've worked this a lot of times. That number ends up getting used um, a lot, as you'll see in the next 2 slides. Okay, calculate the rate constant for the first order reaction. So this is interesting. This is huge. Means we're kinetics. I'm going to take you back over here. Go to kinetics. This is first order. This is second order. This I don't use much, if you remember that in class, but Zero order is not on here because zero order would be the same as first order with the ln's gone. And so what happens here is once you know it's first order, you know over and over again we have to use this equation, which is, I'm loving these ads coming up when I'm trying to lecture, which is the ln, and I'm going to switch to x because they're calling it species x, equals negative kt plus the ln of x sub 0, which is, that means the initial concentration of x, which we just calculated. Now they want you to solve for the rate constant, which is k. So what I'm going to do, and there's a lot of different ways to do this, so you don't have to do it my way, but I'm going to move this guy to this side by adding kt, both sides, because that makes the k positive. And then I'm going to move this guy to the other side. And so when by subtracting natural log of x sub t from both sides, and so what happens is I get kt equals the natural log of the initial concentration of x minus the natural log of the concentration of x at some time. And I'm going to go back to the chart. And then we're solving for k, so I would divide both sides by t. Probably a better way in chemistry to write this, because the factor label method, is the ln of x sub 0 minus the ln of x sub t. And then that whole thing gets multiplied by 1 over t. And so now it's just a matter of plugging in, and I'm going to go back. You guys can still see this, but I'm going to just use these two. So this is the initial concentration of x, 1.2 times 10 to the negative 4 molar. That's the biggest number. Negative 4 is bigger than negative 5. I'm going to use this for, I'm going to use 4.00 times 10 to the negative 5. And the time that it has elapsed between 0 and 35 is 35 minutes. And so what happens is, what I'm going to put here is that k is equal to the natural log of 1.20 times 10 to the negative 4, close the parentheses when you're using the calculator, minus the natural log of 4.00 times 10 to the negative 5. And then that, so I do the natural log of this and then subtract natural log of that, and then I multiply by 1 over 35. And they did have a 0 here, minutes. And so what happens is this has 3 sig figs, and this has 3 sig figs, and this has 3 sig figs, and I'm going to keep 3 sig figs. Probably should only keep 2, because of the fact that when you take the log of a number, only the numbers after count, if you remember from pH, but I looked at the scoring guidelines. And remember, you just have to be within 1 sig fig on the AP exam. And so when I did this on the calculator, I got 0.0313. These are unitless. Taking the natural log destroys the units, but I still have a minute downstairs, which, if you remember, it's always 1 less than the order number. Remember, the power on the concentration is 1 less than the order number, and they said this was first order, and so 1 minus 1 is 0, and anything to the 0 power is 1, and so that is the unit, so 0.0313. Please practice putting this in your calculator. My students over the course of time is like, oh, I see how you set it up. The answer must be right. She wouldn't give us a wrong answer, but it's dicey with these parentheses, so practice. And remember, properties of logarithms, this is equivalent to the natural log of 1.2 times 10 to the negative 4th divided by 4.00 times 10 to the negative 5th, because I just leave it like this because it's 1 less thing to write down. But remember, the log of x minus y is equal to the natural log of x minus the natural log of y. That's one of the properties of logarithms. So if you do this in your calculator and if you do this in your calculator, you should get the same value, and you will. All right, now this next one is calculate the number of minutes it takes the absorbance to drop from 0.6 to 0.600 to 0.075. So interesting, I'm going to go back to the beginning. So the question is, now remember 0.6 is the time, the absorbance at the beginning, and 0.075 is this absorbance, and they want to know what this number is. What is this number when the absorbance has dropped all the way down to 0.075? Remember, the solution's getting lighter. The absorbance, the solution's getting lighter, so more is transmitting and less is absorbing. And so when you come over here, we're solving for t, so always go back to the sheet. The fact that it's first order is the natural log of x at any time is equal to negative kt plus the natural log of x sub 0. Now this is algebra. I'm going to swing and bring this guy here, and I'm going to bring this guy here. And so positive kt is equal to the natural log of x sub 0 minus the natural log of x sub t. And then if we want to solve for time, we have to divide both sides by k. And so what I'm going to just plug in is what was the concentration at the beginning. Time is 0. That's what we solve for in A. It's 1.20 times 10 to the negative 4th. And then I need to subtract this time that we're looking for. What's the concentration when the absorbance is 0.075 is 1.5 times 10 to the negative 5th. So then I have to put 1.5 times 10 to the negative 5th. And then that whole thing has to be divided by k, but I'm going to multiply by the reciprocal of k, which is 0.0313 over minutes. And again, you'll see unitless, 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 minutes is on the top. We're solving for a time. And if you put that in your calculator, you will get 66.4 minutes. Again, I think you should only have 2 sig figs, because remember, but this is what the scoring line has. And remember, when you take the AP exam, I'm going to tell you always keep 3, because they don't dock you if you're within 1 sig fig of the right answer. So you either keep 2, 3, or 4. And so if you always keep 3, you should never lose a point for sig figs. All right, last one. What is the half-length? Include units with your answer. No, half-length or half-life, people, half-length, I love that. Half-life is like, let's say I die at 82. Well, when is half of my life over? At 41. You have to understand that half-life means the time it takes for half of the reactant to be gone. So let's say we're going x to y. At what time will half of x be converted over to y? So again, if you go back to C, this is the equation we're going to use. We're going to use the natural log of x sub 0 minus the natural log of x sub t divided by k. I probably won't do that. But what was the initial concentration? It was 1.20 times 10 to the negative 4. Well, what's half of 1.20 times 10 to the negative 4? It's actually 6.00 times 10 to the negative 5. Looks kind of crazy, but half of 12 is 6. This is to the negative 4. This is to the negative 5. Divided by, oops, I'm not going to do divide by. Let me grab my eraser. Hopefully I don't have to rewrite that. Okay, and then we figured out that, again, K was from part B, 0.0313 over minutes. And so if you do that, you will get 22.1 minutes is half-life. Now, if you'll notice on this sheet over here, they also have this word equation, which is T1 half, this one right here. And I know we probably talked about this in class, even though I haven't taught you guys yet, probably. But this equation comes from the fact, and if you're comfortable using it, you can. The fact that this half-life means that when you use the property of logarithms, sorry, I did that backwards. No, I actually did it right. Sorry. If you do 1.24 times 10 to the negative 4 divided by 6.00 times 10 to the negative 5, because of moving this stuff around, and take the ln of this, it's negative, it's 0.693. That this ratio is always going to be 2. Because of the way I did it, or the reciprocal of a half, because I moved it the other way. But if you do 0.693 divided by 0.0313, you also get 22.1 minutes. The reason I'm not wild about the half-life equation is it only works for first order because of the properties of logarithms. That formula does not work for second order, and it does not work for zero order. And this one always works where you just take the initial and you divide it by half. It's just that if it's second order, you're plopping it into a different equation. All right.